Hello, this podcast is on torque and rotational statics. In this podcast, you'll learn about some key terms involved in rotational motion. We'll learn more about torque, vector multiplication, specifically the cross product, the dimensions and directions of torque. We'll learn about the lever arm, and we'll learn about the requirements for static equilibrium. First, the key terms. Angular acceleration. This is the rate at which a particle's rotational velocity changes. Its symbol is the Greek letter alpha. So we can see angular acceleration is similar to translational acceleration in that it's the rate at which a velocity changes. Angular displacement is the change in a particle's angular position. Its symbol is theta. So it's similar to displacement in translational motion, except position is specified in rotational motion not as a distance from an origin in meters, but in a distance of radians or degrees counterclockwise from the positive x-axis. Angular velocity is the rate at which a particle's angular displacement changes. Its symbol is omega. It too is similar to translational velocity in that it's a rate at which displacement changes. Axis of rotation. This is the internal axis around which a particle rotates or spins. For example, the center of the turntable is the axis of rotation. Cross product multiplication. This is the multiplication of two vectors which yields a third vector that is perpendicular to both of the original vectors. Fulcrum, the point around which an object will rotate, also known as the pivot point. For example, a hinge is the fulcrum or pivot point for a door. Lever, this is the distance between the axis of rotation or fulcrum and the position of the force. Sometimes the lever is an actual object, such as in a seesaw. Other times, such as in a rotating car tire, it's just the distance from the action of rotation to the surface of the tire where the friction force is applied. And here's an example of the lever. This is a seesaw example, but the force B is applied here, so the lever associated with force B goes from the fulcrum to the point the force is being exerted, and it's that distance. So levers are measured in meters, and over here force A is applied a little further from the fulcrum, so you can see that its lever distance is larger. Moving on to torque. It's a measure of the tendency of a force to rotate an object around some axis, fulcrum, or pivot point. Torque is created by applying a force to a lever. It is not a type of force, but it plays the same role in rotational motion that force plays in translational motion. The reason I say that is we know that force causes an object to change its translational motion, and torque, or I should say more specifically an unbalanced or net torque, causes changes in an object's rotational motion. So here's an example of how torque is created. We've got a rolling wheel. This could be a car tire. We have a lever, and that starts at the axis of rotation. It goes to where the force is applied, and of course the force is going to be applied at the edge of the tire where it meets the surface, or whatever is creating the force, and this force is applied in this direction. So the force applied to the lever causes the wheel to rotate, and torque is required for a wheel to rotate. So force applied to a lever causes rotation because it creates torque. Here in the seesaw, we see the same thing. We apply a force. If the torques are balanced, this seesaw will not rotate. It'll just stay motionless. However, if the torque is higher on one side, such as over here, we will see that it will rotate, the seesaw will rotate in this direction about this fulcrum. So torques cause rotation. We have to do cross product multiplication in order to calculate torque, so let's understand what this involves. So torque is equal to the lever times the force, and it's a cross product instead of a dot product. These are two vectors. The lever is a vector and the force is a vector, has both magnitude and direction. And when we take the cross product of it, we are interested in the components of these two vectors that are perpendicular to each other. So we can calculate that by taking the magnitude of the lever, that's the length of the lever, times the magnitude of the force times the sine of phi. And phi is the angle between the force vector and the lever vector. For example, here we have the direction of the lever. Here we have the direction of the lever and its magnitude. And here we have the direction and magnitude of the force vector. Measuring from the lever to the force gives us our angle phi, and that's what we would plug into this equation. Torque is a vector quantity with units of Newton meters, but it's important to note that this is not a measure of energy. I know Newton meters can be used to measure energy. This torque is not a type of energy, even though its units are the same. So we need to remember torque is a vector. I want to take a moment and talk about how we measure this angle phi. It's measured from the lever vector to the force vector, but on our diagrams we will usually have the force vector not at the origin of the lever, but we put it at the end of the lever, at the tip of the vector arrow, because that's the position where the force is being applied. So to measure phi, we need to extend a line beyond the lever and measure from that line. So notice we measure phi in this way, from this line in this direction. With the seesaw, here we have the force of gravity. We have the lever coming out this way, so we would just extend that and we would measure the angle from our extended line of the lever to the force. In this case, this angle would be positive because it's counterclockwise, and we would extend it in this direction over here to find the angle phi for this force. In this case, this angle would be negative because we're measuring it in the clockwise direction. In these cases of the wheel and the seesaw, phi is 90 degrees. So in that case, torque is going to be equal to the magnitude of the lever times the magnitude of the force times the sine of 90 degrees, which is 1, and that just leaves us with the lever magnitude times the force magnitude equals the torque. But that is only when the force vector is perpendicular to the lever vector. And note, the 90 degrees is not, and note that phi is not always 90 degrees for seesaws. It is in this case, but if you look at this case, when the seesaw is tilted, you'll notice that this is less than 90 degrees, and this angle phi is greater than 90 degrees. Let's look at an example of calculating torque for this rolling wheel. It has a lever R and a force is applied to it, F, at the end of the lever. In this example, the force has a magnitude of 10 newtons and it's applied to the top of the wheel in the tangential direction. That means that it will be at 90 degrees or perpendicular to the lever. And the question's asking us, what is the torque if the radius is 2/10 of a meter? So that means the length of our lever is 2/10 of a meter. We take our equation, we plug in the magnitude of our lever, 0.2 meters, the magnitude of our force, 10 newtons, and multiply it by the sine of phi, which is 90 degrees. And of course the sine of 90 degrees is 1. And so this torque applied is 2.0 Newton meters. Before we go any further in our discussion of torque and static equilibrium, I just want us to take a break and review vector multiplication. So we have the dot product and the cross product. So the dot product is a function of the parallel components of two vector quantities. In general, that's vector A dot vector B, and that is equal to the magnitude of A times the magnitude of B times the cosine of the angle phi, and phi is the angle between vector A and vector B, and that gives us the product C. And what's important is this product is a scalar quantity, such as when we calculate work. The cross product is the function of perpendicular components of two vector quantities. So it's different there from the dot product in that the dot product's focused on the parallel components of the vectors being multiplied. Cross product is a function of the perpendicular components of these vectors. As such, it's going to be the A vector cross product with the B vector, and that's going to be equal to the magnitude of A times the magnitude of B times the sine of phi. And it's very important, order does matter in this case. A cross product with B is not equal to B cross product with A, whereas A cross product with B is equal to B cross product with A. And the angle phi is measured from vector A to vector B. And as you can see up here, the product C is also a vector quantity. And interestingly, this vector C is perpendicular to both of the original vectors. So that means it's going to lie on the Z axis. And finally, the right-hand rule determines the direction of the product vector. We'll get into the details of the right-hand rule and how to apply it later on in this podcast. Now that we've reviewed our cross-product multiplication, let's talk about the dimension and directions of torque. Because it's a product of two vectors, its direction is perpendicular to the force lever plane and along the z-axis. So here's an example. We have our lever and we have our force, and that falls in a plane which we'll call the xy plane, and the torque is perpendicular to both. So it is pointing up on the z-axis in this instant. We use the right-hand rule to determine the direction of the torque. It's always going to be on the z-axis, but is it going to be pointing up or is it going to be pointing down? And to determine that, we need to use the right-hand rule. And here's how we do that. You take your four fingers and you point it along the lever. So in this case, the four fingers were originally pointed along the lever, which is in this direction. Then you curl your fingers to point along the force. So notice the force is in this direction and the fingers are curling in that direction. So the hand was originally placed along the lever and then curled in the direction of the force. And when you do that, your thumb will be pointing in the direction of the torque. So in this case, the torque is up, and this is considered the positive direction. And notice that this torque causes a counterclockwise rotation. If we apply the right-hand rule to this sketch over here, we would go ahead and have our fingers pointing towards or pointing along this line of the lever, and then we'd curve them or curl them to point in the direction of the force. And of course, the only way we can do this with our right hand is if the thumb is pointing up. Hence, the torque is in the up direction. Torques that cause counterclockwise rotation are positive in direction, and the torque vector extends above the force lever plane as shown in the sketch below. So here we can see that the torque vector is extended above this plane of the lever and the force. Whereas torques that cause clockwise rotation are the negative direction, and the torque vector extends below the force lever plane as shown in the sketch below. Here we can see in this sketch that the torque is pointing down. Notice if we apply the right-hand rule and we go ahead and put our fingers initially in this direction, and then we need to curl our fingers along the force direction. The only way we can do that is if our thumb is pointing down. It is impossible to have our hands along this line and then curl our fingers this way if our right hand is thumbs up. Moving on, we need to understand what a lever arm is, and that's sometimes called a moment arm. So the lever arm is the portion of the lever that is perpendicular to the action line of the force. In other words, the lever arm is equal to the length of the lever times the sine of the angle phi, where phi is the angle between the force and the lever. So let's look at our seesaw example here. We've got two folks on the seesaw, And this distance r1 is the magnitude of the lever. The force of gravity is applied at the end of the lever, and we can see that it is not perpendicular to the lever. So the lever arm is finding the length of the lever, or the part of the lever, that is perpendicular to the force. And to do this, we go ahead and draw a dashed line along the force, and we extend it upward. This is called the action line of the force. We extend it far enough up so that we can draw a line from the fulcrum to the action line of the force that is perpendicular. So we are drawing from the fulcrum to the line of action a line that is perpendicular to the line of action. And the length of this line is the magnitude of the lever arm. Now our angle phi is this angle here from the lever arm to the force. So we know that this is the opposite side, and that's why the lever arm is equal to the magnitude of the lever times the sine phi. Similarly, on this end, we can do the same thing. We see that the gravity force is not perpendicular to the lever. We can extend an action line of the force down far enough so that when we go over to the fulcrum, we can draw a line perpendicular to the line of action from the line of action to the fulcrum. And this length here is the length of this lever arm. Since the lever arm is defined as r times sine of phi, then another equation for torque is the magnitude of the force times the magnitude of the lever arm. Let's look at an example of how we calculate the lever arms and the torque. In this example, we have a boy and a girl on a seesaw, and we're asked to find the lever arms and torques the two children exert on the seesaw. We're given the distance from the fulcrum, so in this case the fulcrum is in the center of this 3-meter seesaw, and the boy and the girl are at the very ends of it. And we're given that this is a 30-degree angle above the horizontal. We know the force being applied is the force of gravity, so we can calculate that for both the girl and the boy. First, we're going to calculate the lever arms for the boy and the girl. So that's the magnitude of the lever times the sine of phi. That's 1.5 meters times the sine of 60 degrees. To figure out this angle, we have to extend this lever line of action, and we can measure this angle, and it's 60 degrees. Up here, we don't have to extend it. We can go in this direction and measure from the lever vector to the force vector. Both of them are 60 degrees, so both the boy and the girl have a 1.3 meter lever arm. Now let's move on to the torques, and we know that the torque is simply the magnitude of the force times the magnitude of the lever arm. In this case, the torques will not be the same, because while the lever arms are the same, the forces are not, and the boy has a greater torque applied to the seesaw, 764 Newton meters compared to the girl of 637 Newton meters. And so we have an unbalanced torque. We have a net torque in this direction, and it's going to cause the seesaw to rotate counterclockwise until it hits the ground. Let's move on and learn about static equilibrium. An object that is in both translational static equilibrium and rotational static equilibrium is said to be in static equilibrium. Previously, we learned translational static equilibrium is when the object is not moving, acceleration is equal to 0, the sum of the forces adds up to 0, and the velocity is 0. Notice as I go over rotational static equilibrium, the similarities with translational static equilibrium. The object is not spinning when it is in rotational static equilibrium. That means that the angular acceleration is 0. The sum of the torques is equal to 0, so there is no net torque, and the angular velocity is 0. When adding torques, we need to remember that counterclockwise is the positive direction and clockwise is the negative direction. And that means when we have no net torque, or in other words, the sum of all torques is equal to 0, another way of writing that is the sum of the torques that cause counterclockwise rotation have to be equal to the sum of the torques that would cause clockwise rotation. Let's look at an example. Where should the 60-kilogram boy sit on the seesaw in order for the system to be in static rotational equilibrium? So here we have our board, our seesaw. It's 6 meters long. We know that the girl is at the end of it. The fulcrum's placed in the middle. So the girl is 1.5 meters. That's her lever. Her mass is 50 kilograms, applying a force of 490 newtons at the end of this lever. The boy's mass is 60 kilograms, applying a force of gravity of 588 newtons at some point on this lever. The seesaw has a weight of 150 newtons. The first step in solving this problem is to set up the governing equation, and we know for static equilibrium the torques need to add up to 0. Everywhere you have a force applied, you're going to have a torque. So the first thing you need to do is draw a force diagram and identify all the locations of the forces. So we have a torque created by the boy, a torque created by the seesaw, and a torque created by the girl. Now we can use our equation here, and we can find out that the boy's torque is going to be equal to the force of 588 newtons times this length L, the length of the lever, plus 150 newtons, which is the weight of the seesaw, times its lever, which is 0. So in this case, the seesaw does not contribute a rotating torque, and that's because the fulcrum is at the seesaw's center of mass. If the fulcrum was not at the center of the mass, if it was to the right or left of the center of the mass, then there would be a lever distance, and the seesaw's mass or seesaw's weight would cause a torque. And we need to subtract 490 newtons times 1.5 meters, which is the girl's torque. And the reason we're subtracting that is if you look at this force, the girl's force of gravity, it will cause the seesaw to rotate in the clockwise direction, and that's a negative torque. We can rearrange this equation to solve for L, and we find out that the boy should sit 1.25 meters from the fulcrum to put this seesaw system in static equilibrium. There's a second part to this problem, and that is, what is the normal force the fulcrum exerts on the seesaw? So we take a look at this, and we know that the forces have to sum up to 0 because this seesaw is not moving translationally either, so the forces are balanced. We have the force of gravity of the boy, the force of gravity of the seesaw, the force of gravity of the girl, and I didn't draw it here, but we have the normal force pushing up on the seesaw. The sum of these four forces equals 0, so we can rearrange this equation to solve for the normal force, and that gives us this expression. We can plug in our values for the gravity forces, and we find out that the normal force the fulcrum is exerting on the seesaw is 1,228 newtons. We're going to close this podcast by studying two special cases for static equilibrium. In the first case, we have two forces acting on an object, and for these two forces to create static equilibrium, the forces must be equal in strength and opposite in direction and lie on the same line of action. So let's look at this wheel, and we would have a lever in the middle here. And so the forces have to be equal in strength and opposite in direction, plus they have to lie on the same line of action. Let's take a look at why they have to lie on the same line of action. If force 1 was moved up here closer to the center, its lever would still be the same, because any distance from the center of this circle to the circumference of the circle is going to be the same length. However, the angle between the force and the lever would be different, and that means that this lever arm would be shorter than this lever arm. So the torque creating the counterclockwise rotation would be greater than the torque causing the clockwise rotation. If we move this force F1 up above the midpoint, up somewhere in this region, even though the force is pointing in the opposite direction of F2, because it went to the top half of this wheel, this force would actually be causing torque in the same direction as the F2 force. In other words, this torque would be contributing to the counterclockwise rotation. So the same analysis holds true for F2 if we moved it closer to the center or moved it above the center line. So it's important that these forces lie on the same line of action in addition to being equal in strength and opposite in direction. Our second case involves three forces, and here there's two possibilities. The first one is the lines of action of the three forces intersect at a common point. So here's a case where we have three forces, and if we extend their lines of action back through the wheel, we'll see that they intersect at a common point. The other condition is that the forces are all parallel to each other. So here we have three forces. Their lines of action are not going to intersect, but they are parallel to each other. And in both instances, the forces have to add up to zero. So in this example over here, since these forces are parallel to each other, these two forces have to add up to be equal to the magnitude of force 1. Down here, the forces are not parallel to each other, so we would have to take all three of these forces and break them into their vertical and horizontal components, and then the vertical components and horizontal components of all three forces would have to add up to 0. So these are just two special cases of how you can achieve static equilibrium. This wraps up what we want to learn about torque and static equilibrium. Before we go, let's quickly review what we learned. In summary, torque causes a particle or objects to rotate. Another word for rotation is spin. It plays the same role in rotational motion as force plays in translational motion, but torque is not a force. Torque is created by applying a force to a lever. Torque is a vector quantity, and it's calculated by doing cross multiplication between the lever vector and the force vector, and that gives us, and that is equal to the magnitude of the lever times the magnitude of the force times the sine of phi, where phi is the angle measured from the lever vector to the force vector, and that in turn is equal to the force times the lever arm. Positive torques cause counterclockwise rotation, negative torques cause clockwise rotation. Static rotational equilibrium occurs when an object is not rotating or spinning. The conditions for that, the torques have to sum up to 0, the angular acceleration needs to be 0, and the angular velocity needs to be 0. Note the similarity to translational equilibrium. The forces have to sum up to 0, the acceleration is 0, and the velocity is 0. Hopefully through this podcast you saw some similarities between translational motion and rotational motion, because being able to identify these similarities will help you grasp the concepts of rotational motion and how to analyze it. Well, this ends our podcast. I hope you found the information helpful, and have a good day.